find linear ones yourself. The other ones are, you probably want a little more experience with algebra to be able to do those comfortably. So let me just show you the basic idea. So here's the central idea. So as I said in the last topic, the key to finding the inverse of a function or relation is to switch the roles of x and y. So let me go ahead and draw the same picture I've been drawing the whole time. So if I have these guys are x's and these are y's, then if I have an x here and I have a function that takes it over here, then, so I'm thinking of this as a particular x. I'm going to call this one a, I guess. If I take this a and I do f to it, I get b, right? So this guy is a over here, and this guy is b. If I then do f inverse to that, to b, I get right back where I started from, right? I take b and I go the other direction, back to a. That's what inverse functions do. So the thing I want you to see here is we're essentially switching the roles of x and y. If f of a is b, then f inverse of b is a. So we just switch all the x's and y's essentially in our function, and that's how you find the inverse. So what we're going to do to actually algebraically find the inverse is we're literally going to switch the x's and y's, and then to get it in f of x form, we're going to solve for y, because that's f of x. So let's see an example of that. So let's say I have f of x is 3x minus 9, and I want to find the inverse. Well, what I'm literally going to do is switch the x's and y's. Now, one thing to remember is that f of x is y. Right, f of x is just another name for y for us. So this really says y equals 3x minus 9. So I haven't done anything yet. All I've done is rewrite it. Now I'm actually going to do something. I'm going to switch x and y. So I'm going to replace all the y's with x's and all the x's with y's. You might ask yourself, is that a thing you can do? It is, because I'm looking for the inverse. So that's the operation where I'm finding the inverse, is I'm switching the x's and y's. So this new thing that I've got here actually is the inverse of that one. But because we want to think of the x's as inputs, I'm going to go ahead and solve for y. So I'm going to get it into y equals some function of x form. So add 9 to both sides. Divide by 3. I'm going to turn it over so it's y equals instead of something equals y. There you go. We could rewrite this if we wanted to. I could split this up into x over 3 plus 9 over 3 is 3. I'll write it in a couple steps. But in all honesty, I would probably stop here, especially for inverse purposes. I don't know if you remember a couple topic videos ago when we were getting introduced to inverses. At the end, I showed you how how f and f inverse kind of take each other apart. Like if you do one to the other, like you in function composition, you put one inside the other one, all the layers just get peeled off one at a time. And that's the case here too. But I like this, like I've got times 3 minus 9, right? I'm doing that in order, times 3 minus 9. So the opposite operations would be plus 9 divided by 3. So we get plus 9 divided by 3, right? Exactly like we'd expect. So I would write this as f inverse of x equals x plus 9 over 3. Or if you prefer, 1/3 x plus 3. Either of those is fine. So let's see what that looks like. Now, in the last topic video, I mentioned that, let's see, do I have this up for that one? Yeah, it's this one. I mentioned that what it looks like is all the points getting reflected over the line y equals x, which it is. So I've graphed the line y equals x. It's a little faint here, but I hope you can see it there. And here is y equals 3x minus 9. as we'd expect, y-intercept -9, slope of 3, nice and steep upward. And so here is me just writing x equals 3y minus 9. Literally the same thing. I just switched the x's and y's, just replaced all the x's with y's and vice versa. There it is. If I then write this as y equals, what was it, x plus 9 over 3, you can see that that's the same line, right? That's clearly the same line. So all I did was sort of write it in the form we're more familiar with, y equals, so that this guy is f inverse, right? I could write f inverse of x equals x plus 9 over 3. And that's literally the same exact thing as just switching the x's and y's. And I just kind of wanted to point out what that looks like in other contexts. So here is y equals square root of 2x plus 5. I've written as f of x equals square root of 2x plus 5. And here in the next line, all I did was the exact same thing. I just said x equals square root of 2y plus 5, right? I just switched the x's and y's. And lo and behold, look what happens, right? It's reflected through the line y equals x. I even plotted a few points here so that you could see them. Put them in orange so they'd be nice and visible. And you can see that 2.646 is on f, so 2.646 comma 1 is on f inverse. And 3.317 is on f, so 3.317 comma 3 is on f inverse. And you can see the points all kind of define this this function. Similar for the other one, right? 10.5 is on f, so 5.10 is on f inverse. Right, and so on for the other functions too. Let's get to some nice messier ones. So here's one. Right, and so you might say to yourself, how are we going to mirror this thing through the line y equals x? Well, it's going to look like this, right? So there's a few points I've got on here, right? This one's on is on f or on g. This is on g. This is on g. So if 3.8 is on g, then 8.3 should be on g inverse. If 1.2 is on g, then 1.21 should be on g inverse, and we see that it is. Right? You can see the nice mirroring that's going on here. Let's do one more. I spent time making these. I want to show you my pretty graphs. So here's a funny looking one, right? What's that going to look like when it gets mirrored? Well, it's going to look like this, right? And you can still see that pattern of, or you can see that nice pattern of like there's a point here, corresponding point there, right? So we get something like this, right? I picked a few points there. Did I not do the tens? Whatever. Yeah, so you can see point here turns into a point there. Point here turns into a point there. Point here turns into a point there. Right? So they're all it's just mirror images through the line y equals x. Let's do one more linear example. It'll be relatively quick, and then I think we'll be done. Actually, finding inverses is pretty easy. Like there's not a lot to it. We're going to do the same exact thing. I'm going to write. I'm going to take this function. This is y, so I'll write it as y. Switch x and y. Solve for y. We're going to do that every time. So let's do something with some fractions, right? So let's do like y equals 1/2 x minus 5 over 4. How's that? That looks pretty bad. So I will switch x and y, or excuse me, I suppose I should probably have written this as f of x, since we're using function notation here. I want to actually do that. So f of x is 1/2 x minus 5/4. So that's y is 1/2 x minus 5/4. Switch x and y, x equals 1/2 y minus 5/4. Now I want to solve for y, so I'd like to get rid of the fractions. I'm going to multiply everything by 4. 4x equals 4 times 1/2 is 2, so I got 2y minus 5 here. To solve for y, I'm going to add 5 to both sides. Let's come up here. So I got 2y equals 4x plus 5. So I divide everything by 2. We get y equals 2x plus 5 over 2. And that is my inverse. F inverse of x is 2x plus 5 over 2. And that's pretty much it. So I guess maybe we should see that on Desmos real quick and then be done. So we got 1/2 x minus 5/4. Where's my Desmos here? So turn off my fancy graphs. So here we have y equals 1/2 x plus 5/4. There's that guy. Was it 5/4? I did minus 5/4, right? I don't remember. I'm sorry. I'll have to flip my share back to the whiteboard. It was minus 5/4. Okay, and then we got 2x plus 5/5. Now, there's the thing I'm going to be finding the inverse of. So we've got y equals 2x plus 5/2. We got that one. That looks right to me, right? That's a nice mirror image. So there you go. That's basically all there is to it when you're finding inverses of linear functions. Switch x and y, solve for y, and that's it. Then you're done. Now, for these other ones, for these other functions, like these wouldn't have nice inverses that you could find easily. But I did want to point out that don't think that just because some function doesn't have an inverse that is a function, that it doesn't have an inverse, right? It does have an inverse. There it is, right? You just switch the x's and y's. It's just that this inverse isn't a function, so there's not good notation, and it's really hard to solve for. So we're not even going to worry about those. But every relation has an inverse relation. You just swap all the x's and y's, and there you go. That's the inverse. It's just that it's not always a function, so it's not always easy to solve for. And I think that is probably just about all I want to say about finding inverses algebraically. I actually think this is the easiest thing to do of the things that we've done. Like conceptually, inverses are kind of interesting and a little bit tricky. But the actual mechanics of finding an inverse are not that hard. So if it's written in f of x form, write it as y equals some function of x. Switch the x's and y's. So replace all the y's with x's and the x's with y's. Solve for y, which sometimes can be pretty hard. That's where most of the work is. For linear functions, it's never going to be that hard. You might have fractions, but that's about as bad as it'll get. And then rewrite as f inverse. That's it. That's how you do it. It's a 4-step process. F of x becomes y, switch x and y, solve for y, rewrite as f inverse. That's it. That's how you do it. So that's all I really want to say about this. So I will see you guys in the next video.